So we've seen that there are certain patterns that happen again and again when we're computing with lists. Combining elements, transforming elements, selecting elements. So let's see how those are turned into functions which we'll call map and filter and reduce, or in fact as it's called in Erlang, fold_r. So let's start off with the example of finding the area of every shape in a list. Remember, this was how we defined the function. All areas on the empty list returns an empty list. All areas on xcons x's returns a list whose head is area of x and whose tail is all areas applied to the tail. So we get the same number of elements, and to each element we apply area of x. Now, looking at this definition, what is specific about, what tells us that this is about areas, apart from the fact that the function is called all areas? The only thing that is specific here is applying the area function, and we see that there. So everything else is generic. It's saying take an empty list to an empty list, and as we're running through the list, for each element apply this specific function. So what we can do is transform that into a generic function, and we pass in the area function to be applied as the first argument. So now we have the map function. It takes two arguments. The first is a function, the second is the list as before, and instead of applying area to the head, we apply the function f to the head. So here we've got a function is the value of the variable, and to apply that function we simply do f open parentheses x close parentheses, and that gives us our higher order function. It now takes a function f as an argument, and you can see we've just got to remember that in the recursive call we again call map with that second argument. Now, how do we reconstruct our original function? Well, the answer is we get all the areas applied to a list called shapes by applying map to, as a second argument, shapes. But here you see the first argument is the area function. Now, this might be, the notation we use here is slightly different than you would see in other languages. We have to say, we don't just write area, the atom here, because that area, even though it's a name of a function, it is in fact an atom. So we have to say, what we mean here is a function, so we say fun area, and also we have to say the arity, so we say fun area /1, because we mean area, the area function of arity 1. So we signal it's a function and we say it's arity. But there's our definition. So now, given map, we've got a much simpler definition of all areas. Now, why might we want to use a pattern like this? We've got the pattern of map. Why do we want to implement these patterns? What are the advantages we get? Well, I think there are at least two different advantages. One is we get reuse. We define map once and we get to reuse it again and again and again. So it's there, in fact it's in the standard library, so we don't have to define it at all. It's just there. But I think the second reason is perhaps the more important one. It doesn't take long to define a map for ourselves. But the crucial thing about using the built-in map, or calling this an application map, is that we make our definition that much more comprehensible. When we see a map, we know what's going on. We don't have to understand the recursion, we just know we've got a map. What we're doing is applying this function to every element of the list. There's nothing more to understand. And that is neat. So I think those are two. We get reuse, and of course reuse is something that every programmer likes, but also we get comprehensibility. So you understand your code when you come back to it in a few months' time, and somebody else reading your code will find it that much more understandable if you use that standard higher order function. Okay. So our second argument, our second example was the example of finding the circles in a list of shapes. So what we did here was we had to do a pattern match in order to see whether a circle, whether a shape, the shape at the head of the list, was a circle or a rectangle. Now if we just take a look at this, you can see that what is specific here is this particular application of pattern matching. That's where we distinguish between circles and rectangles. Everything else is boilerplate. We take circles, take an empty list to an empty list, and what we do on the tail of our non-empty list is always apply the same function again. It's just a standard recursion pattern there. But what we do is we have to distinguish between those two cases. Now how can we extract something general from this? What we do is we think the general case of distinguishing between two cases is summarised by a function which is a property. What is it? How does a function represent a property? Well, the answer is it represents a property by giving the answer true or false when you apply it to an element. So if P is true, the element has the property. If P is not true, P is false, the element doesn't have the property. And now you see very clearly here that what we have done is we now passed in a second argument. In fact, it comes first, the argument P, the property, and then the second argument is a list again, and filtering the empty list gives us an empty list, but filtering the list x cons x's, we have a case switch according to whether or not P of x is true, in which case x is included in the result, or P of x is false, in which case it isn't. And in either case, we attach the x or not to the result of filtering the rest of the list, filtering the tail with P. So again, you see that pattern that was there in our definition of circles, but it was mixed up with the particular pattern match. So how can we recover our definition of circles using filter? Well, the answer is we can factor out that test into a function isCircle, which I've done here. So isCircle, when applied to a circle pattern, gives us the answer true. When it's applied to a rectangle pattern, it gives us an answer false. And then we're able to apply filter to that fun isCircle and shapes to filter a list of shapes. And again, you can see how I've called the function. It's a function that's already defined. So what I have done is give the function name and arity and say, I mean this to be a function. So I say fun isCircle and arity1. So there we have our original definition. And again, just as I hinted when we defined the defined map, we're getting reuse here. We don't have to redefine filter each time, and also we're getting comprehensibility. We know this is a filter. So it's clearly a good thing to do this. Excellent. Okay. So let's move to our final example, and that was taking the sum of a list of numbers. And again, let's ask this question. The sum of an empty list is 0. The sum of x cons x's is x plus the sum of x's. What are the specific things, the summy things about this definition? And the answer is there are two. The starting value is relevant. That's not generic. That's a specific starting value. And the combining function plus is specific. So we've got a starting value, and then we've got a way of combining the sum so far and the next value. And this is how we can define this as a general function. I've called it reduce here. As I said earlier on, that in the lists module, it's lists fold R, F-O-L-D-R. And how does this work? Well, reduce takes 3 arguments. It takes the combining function, it takes the start value, and it takes the list. And for an empty list, it just returns the start value. For a non-empty list, what does it do? Well, it combines the value at the head, x, with the result on the tail. And that is reduce applied to combine and start and x's. So that's precisely what was implicit there in that definition of sum. And then we can redefine sum here as reduce applied to the fun plus the functionality 2, so it combines values together, 0 and the list x's. Now what we could have done, in these three examples I've applied reduce to I've applied the higher order function to a named function. We could equally well put a lambda in there. We could say fun, open parenthesis x comma y, close parenthesis, arrow x plus y, end, and that would allow us to define sum in exactly the same way without having an auxiliary definition there. And we'll come back to that sort of fun expression, that sort of lambda, in the next section of the MOOC. But just to recap, in fact I've done it there, apologies. So what we're seeing there is there we see that example. Now just to move on to recap, you can see that these higher order functions, if you're thinking of an example, you can imagine processing a collection of web pages using map, and something of processing each element on a page using map again, and then selecting certain elements using filter and combining those sets of values into a single value using reduce. So these map reduce frameworks take these functions from functional programming, that's where they came from originally, and they scale them up into a framework which can do very efficient, very effective data processing. So we can see these things are not just a curiosity, but they're useful in practice. So what we're going to do now is get a bit of practice using higher order functions, and then what we'll do in the next section is put them to work to do even more for us. One thing you might like to think about is how we could apply the functions that we've written here to do some of the things we've already done last week. So you can see that I've done it for some of the examples. In the homework you're going to look at in a minute, there are some other examples. But you can look again at the work that you've done and think, okay, how could I apply these higher order functions in a way to improve my functional programming practice? And that's something, I guess we're always improving, we're always getting new techniques to solve older problems, and it's often interesting to revisit those problems when we have some new techniques and see how they might be. We might improve our solutions. Okay, now it's over to you to do a bit of work, and then at the end of this section I'll recap and run over one or two solutions. Okay, that's it for now. Thanks.